You might wonder why color deserves a whole lecture in this course. The reason is that in visualization, color isn't just decoration, it is information. Every color you choose either helps your audience understand the data more quickly or distracts and mislead them without you realizing it. By the end of today, you will have a clear, systematic approach for every color decision you make in any chart or dashboard. My goal here is to help you move from using color by instinct to using it as a deliberate design choice. Let's get started. Let me walk you through the 5 learning outcomes of this lecture. They are designed to build on each other. First, we will look at why color can be both helpful and risky in visualization. Next, we will talk about the difference between how color appears on a device and how our brains actually see it. These are not the same thing. After that, we will learn the main types of color palettes and which ones fit different kinds of data. We'll also look at 2 common mistakes: using rainbow colorams and red-green encodings. Finally, we'll bring everything together into a design approach that is accessible and easy to repeat. Keep these 5 outcomes in mind as we go through the lecture. They are your go-to checklist. So, why does color deserve a full lecture? Let's think about it. It is the most memorable visual channel, but also the easiest to misuse. Research shows that precision along a scale is better than color for precise quantitative comparisons. So color should be your first choice for exact values. However, for grouping, highlighting, and spotting patterns quickly, color is extremely effective when used properly. The challenge is that color theory now involves several fields, including psychophysics, accessibility standards, cartographic design, and display technology. Here's something important. The same hex code can look very different on 2 screens. This isn't a minor detail, it's a key design issue. So a hex code is the numerical value given to identify a color. So we can decide what is the color based on the hex code and vice versa. The main principle to remember is that if a color difference doesn't match a real data difference, viewers will look for meaning that isn't there. So if I look at the slide here, a scatter plot with one highlighted outlier, for example, a choropleth means a map that shows in single color a particular class, showing a regional gradient or a heat map revealing block structure becomes dramatically clearer with proper color. The same visualization becomes misleading when the palette introduces false boundaries. Now, as I told you, if the palette is giving some misleading information, then we will not be able to understand what is actually shown in the visualization clearly. So this implies an order where none exists or fails for viewers with color vision deficiencies. So that's why the modern color theory spans multiple disciplines. Now, the central principle, anyway, is in color in visualization should be chosen to support a specific analytical task. If a color difference does not correspond to a meaningful data difference, the viewers will search for meaning that is not there, increasing the extraneous load or cognitive load as we discussed in our previous lectures. So this slide contains a lot of text because you need to understand the reason why color deserves a full lecture. Before we talk about how to choose color, let's discuss when it is better to remove it completely. Sometimes that's the best design choice. The first trap when we are dealing with color is over encoding. For example, let's say we have a bar chart and we apply different colors to the element, but that's a false lead. If bars are already separated by position and labels, adding different colors just creates visual noise without adding any information. The next one is the highlighting method. It is more focused. Use gray for everything except the one data point you want your audience to notice. Another most widely used case is direct labeling. Direct labeling works especially well for line charts. If you label each line at its end, all lines can use the same neutral color without causing confusion. If you remember our previous lectures, we had the line charts labeled to avoid those extraneous loads. Another one is small multiples. They can turn a messy spaghetti looking chart into a very clear readable panels. If you remember the previous lecture, we talked about this. Treat color as a resource to use carefully, not something to add just because the tool makes it easy or you think that this color looks nice. Let's think about how color actually is generated. Let's establish the mechanism. Color starts as light, electromagnetic radiation, but our experience of it is entirely constructed by the brain through two-layered processes. First is known as trichromatic sensing. Three cone types respond to different wavelength ranges. Then opponent processing takes over. Computing contrast, which is the light versus dark, red versus green, blue versus yellow, these things happen in the computing contrast stage. The perceptual attributes that matter for design are hue, lightness, and chroma. Now, this is a practical point. The HSL and HSV sliders in your visualization designs, you may see this in different software and you may have already seen this in elsewhere. These are approximations of these dimensions. What I try to say here is that there is a difference between the device and the way that you or any viewer as a human perceive the color. So in this case, whatever that is being observed, the dials, the numbers, they are not perpetually uniform, and then they are not perceptually uniform. Moving a saturation slider by 10 units, for example, at one end of the scale looks very different from the same move at the other end, which means you do the change at let's say at the beginning, the color change would be different to what you see at the end. Color spaces like Scilab were specifically engineered to fix this, to align the numerical distance with the perceptual distance. The amount that you change according to the slider is the amount that you actually perceive. Device color and perceptual color are fundamentally different concerns. So when you are designing, make sure that you understand this concept. Every color decision you make maps onto one of these three perceptual dimensions. Understanding them gives you a vocabulary for deliberate design choices. The first one is the lightness. It is the most powerful channel for conveying order. This is the dark is more biased, and it's why sequential palettes work so naturally. Hue is what most people think of as color. Red, blue, green, yellow. But notice what hue fundamentally cannot do. It cannot encode quantity. Viewers have no shared sense of how much more blue something is than green. Hue is for categories, not amounts. Color is for categories, not amount. Finally, chroma, or the saturation. It controls attention. Bright, vivid colors pull the eye. Desaturated, muted colors support context without competing for attention. Use this hierarchy deliberately. Emphasize your signal with saturation. Order your data with lightness. And separate categories with hue. Color can do several jobs in a single chart at once, showing data values, separating groups, highlighting outliers, organizing the layout, etc. That's fine. But the discipline is keeping those roles from bleeding into each other. Here's a simple example. If red means outlier in your chart, it can't also show up as a random category color elsewhere in the same figure. Your reader will assume every red mark is an outlier because that's the deal you made with them. Think of color as a kind of visual grammar. Every color choice is a promise, and breaking it quietly confuses people in ways they might not even be able to articulate. The good news is there's a clear mapping between task and strategy. Showing group membership, then use distinct hues. If you want to show magnitude or quantity, use a light to dark sequential scale. If you want to show deviation from a midpoint, use a diverging palette. Showing something cyclical or periodic, use a cyclic palette. Drawing attention to one thing is your objective, then use a single accent color against a neutral background. The question to ask yourself at every step is simple. Does this color correspond to a real difference in the data? If you can't answer yes, it is worth reconsidering the choice. We have now reached the practical core of the lecture. Palette families. Every palette in any visualization tool fits into one of these categories, and picking the wrong family is the most common big mistake in chart design. Categorical palettes use different hues to show groups with no natural order, like countries, product categories, or species. Sequential palettes use a lightness gradient to show quantity, where lighter means less and darker means more. Diverging palettes use two hues that meet at a neutral center for data with a meaningful midpoint, such as surplus and deficit or values above and below an average. In the next three slides, we will look at each type in more detail. Remember this three-way distinction. It is the key decision you make before picking any specific color palette. Let's go deeper on categorical palettes. When your data is nominal, meaning it has no natural ordering, your design goal is equal perceptual salience across all categories because there is no order. You are just using the color to show nominal data. No color should pop more than the others unless you intend one category to stand out. That requires carefully balancing lightness and chroma across your hues, not just picking whatever colors look visually interesting. The critical constraint is the 5 to 7 color limit. Beyond that, viewers might look back and forth between the legend and the chart so frequently that the cognitive cost outweighs the information gained. A clear failure. For colorblind safe defaults, two palettes consistently come up in the literature are called Color Brewer's Set 2 and the Okabe To palette, which was designed specifically for deuteranomaly, the most common form of color vision deficiency. If you are building any public facing visualization, start with Okabe color design. Sequential palettes encode order and quantity, population density, temperature, risk levels, income, these kind of variables. The perceptual mechanism is lightness. Viewers reliably interpret darker as representing more. This is not a cultural convention, it is a fundamental feature of the human visual system. Your palette must therefore have monotonically increasing lightness, not just a shifting hue, that's not changing color. A single hue ramp, which is a single color, light blue to dark blue, for example, is the simplest approach. Multi-hue ramps like Viridis or YIORRD add perceptual discriminability over longer ranges while still maintaining lightness order, making it easier to distinguish values that are close together. Both Viridis and blues are also colorblind safe, making them strong defaults. The mistake to avoid is using a sequential palette on nominal categories, which implies a ranking that isn't in the data. So be careful of that. Before you do your visualization, make sure that you understand whether the data is nominal, categorical, or ordinal. There is an order. Always confirm that. Does my data have a natural order before reaching for sequential? Diverging palettes are the right choice when your data has a genuine, meaningful center. A true zero, a target value, a historical average. Budget surplus versus deficit is the textbook example because there is a center point. Temperature anomalies relative to a long-term baseline is another example. The design structure is two contrasting hues, two contrasting colors, say red and blue, that radiate outward from a perceptually neutral midpoint, typically a light gray or white. Both arms of the palette should carry equal visual weight unless you deliberately intend one extreme to appear more significant than the other. You might have seen this visualizations in different cases where they promote some products or discuss about extremes in climate or weather patterns. Color brewers RDBU, BRBG, and PIYG are well validated choices for this case. They are all colorblind safe. The critical rule I want you to remember from this slide is that never use a diverging palette without a genuinely meaningful midpoint. If your data doesn't have a special center value, the neutral color will imply one that doesn't exist. So it's a psychological thing. Make sure that you understand what you really want to deliver. Two more palette families complete our vocabulary. Cyclic palettes handle data that wraps around. Compass bearings, hours of the day, phase angles in a signal, etc. The defining design constraint is that the two ends of the palette must connect smoothly, with no sudden perceptual jump. If you use a sequential palette for wrapped data, you will create an artificial visual boundary at the wrap point that doesn't correspond to any real discontinuity in the data. So the viewers will misinterpret it. Accent palettes work on a completely different logic. They are not for encoding multiple categories, they are for directing attention. One or two vivid accent colors within an otherwise neutral grayscale tone chart pull the eye exactly where you want it to be. No legend needed. The visual hierarchy does the work. One strong, consistent accent is far more powerful than many competing colors. Remember that. Think of this table as your go-to cheat sheet every time you pick colors for a chart. Each row covers one color family, what kind of data it works best with, when to use it, and one key mistake to watch out for. That last column is worth a close look. Each warning points to a really common pitfall. Too many categories, more than 7, and your legend becomes a mess nobody wants to read. Sequential colors on unordered data, it accidentally suggests things have a ranking when they don't. Diverging colors with no clear midpoint, it makes one value look special when it is not. Swapping cyclic for sequential, it creates a break in the data that simply doesn't exist. Reusing accent colors for different things, it confuses your reader because you have already promised them that color means something specific. Come back to this table whenever you are choosing a color palette. It's a quick sanity check that'll save you from the most common mistakes. Let's talk about the rainbow color ramp. Probably the single most common mistake in scientific visualization, and one that is surprisingly easy to make since it's still the default in a lot of software. It looks great at first glance, it is bright, it uses every color, and it feels expensive. So what's the problem? It tricks your reader's eye. Rainbow colors don't get lighter or darker in a smooth, consistent way as you move across the scale. Instead, the brightness jumps up and down, and your brain interprets those jumps as real boundaries of features in the data, even when there aren't any. Yellow and cyan tend to pop more than they should, while other transitions get visually squished. The result is that people see patterns that aren't actually there. The good news is that there's a family of color scales built specifically to fix this. Viridis, Plasma, Inferno, Magma, and Cividis. They all shift smoothly from light to dark. They work for colorblind viewers, and they let the actual data speak rather than adding visual noise. The rule isn't a flat out ban on rainbow. It's that you should be able to justify it. Ask yourself, does it suit the data type? Does it support the task? And is it accessible? If the answer is just it looks nice, that's not enough of a reason. This table helps answer a very practical question. Which color space should you actually be working in? RGB and hex codes are ones you can't really avoid. They are how colors get specified for screens and web outputs. But they have a hidden problem. Tweaking RGB values by the same amount doesn't produce changes that look equal to your eye. Some shifts feel dramatic, others barely noticeable, even when the numbers say otherwise. HSL and HSV feel more natural to work with. Think of those sliders in a color picker. But they have the same underlying issue. The numbers still don't match what your eye actually perceives. CLAB and LCH were designed to fix exactly this. The whole point was to build a color space where equal numerical steps look like equal visual steps. That makes them the right tool for building and thinking through a color palette. The maths actually lines up with what people see. OKLab and OKLCH are newer and improve on CLAB in a few ways. They are starting to show up in CSS specs and modern design tools, so they are worth knowing about. The practical workflow is simple. Think and reason in CLAB or OKLab. Then export in RGB or hex when it is time to actually use the colors in your charts. Use the right space for the right job. Here's something that catches a lot of people off guard. Color doesn't exist in a vacuum. The exact same hex code can look noticeably different depending on what's around it. This is called simultaneous contrast. And it is not a monitor glitch or a software bug. It's just how human perception works. A medium gray square looks lighter when it sits on a black background than when the identical square sits on a white one. Same color, different surroundings, different experience. For chart design, this has a real practical consequence. A palette that looks perfectly balanced on a white canvas in your design tool might shift visually when it lands on a dark dashboard or when it gets projected in a conference room. The colors haven't changed, but they look like they have. The rule of thumb here is to keep your backgrounds neutral and consistent, and crucially, to test your palette in the actual environment it will be seen in, not just inside your design application. One more thing worth flagging, be careful with transparency. Semi-transparent marks have a sneaky way of implying that opacity means something, that heavier or darker areas represent larger values. For example, readers will naturally start looking for meaning in that visual weight, even if you never intended it to carry any. If your transparency isn't encoding real data, it is likely creating confusion you didn't plan for. Around 8% of men and 0.5% of women have some form of color vision deficiency. That might sound like a small number, but put 50 people in a room and roughly 4 of them can't reliably tell red from green. That's worth sitting with for a moment. Because red and green are still the default color pair on financial dashboards and status indicators almost everywhere. Pass and fail, profit and loss, up and down. The most common deficiency type, deuteranomaly, is exactly a red-green deficiency. So those charts are effectively unreadable for a meaningful chunk of every audience. The easy fix is to swap in blue and orange as your default pair. These two remain distinguishable under virtually every common type of color vision deficiency, with no real downside for everyone else. For checking your work, two tools are particularly useful. ColorBriver certifies palette RAMs as accessible from the ground up. VizPalette lets you preview any palette through simulated deficiency conditions. So you can see what your readers actually see. And if you genuinely can't change the colors, say because a brand system locks them in, there's still a fix. And redundant encoding, pattern fills, varied line dash styles, or labels mean the information survives even in grayscale. But remember about the extraneous load. Color becomes nice to have rather than the only thing standing between your reader and understanding the chart. Let's get concrete and look at the charts you are probably making most often. Bar charts resist the urge to give every bar a different color. It's a really common instinct, but if your bars are already telling the story through their position and axis labels, adding multiple colors just creates visual noise without adding any real information. The better move is to use one neutral color throughout and accent only the bar or bars that carry your actual message. Line charts, color has to work harder here because thin lines need stronger contrast than filled areas do. Combine color with direct labels at the end of each line rather than relying on a separate legend. And if you find yourself with 5 overlapping colored lines all fighting for attention, seriously consider whether small multiples, like separate mini charts side by side, would actually be clearer. Often they are. Heat maps is where color genuinely earns its keep. It's excellent at surfacing patterns and extremes at a glance in a way that numbers alone can't. The catch is that readers struggle to extract precise values from color. They can see that something is darker, but not exactly how much darker. If your precision is important, if precision matters, add text labels directly to the cells. And when you do, always check that those labels have enough contrast against whatever color sits behind them. It is an easy thing to overlook and a frustrating one to get wrong. Picking the right palette family starts with one question. What kind of data are you showing? If it is categorical, for unordered groups with no natural ranking like regions, species, or product lines, the goal is to make each category visually distinct without letting any single color dominate. Watch out for one hue that feels heavier or more attention grabbing than the rest. That's an accidental hierarchy you didn't intend to create. In the case of sequential, like for data that runs from low to high, like temperature, population, or revenue, the key is a smooth progression from light to dark, or vice versa. Because our eyes are much better at reading lightness changes than hue changes alone. A good sequential palette feels like it naturally goes somewhere. In the case of diverging, like for data that has a meaningful middle point with values pulling in two directions on either side, like above and below average or gain and loss, the midpoint should look visually neutral. Neither arm of the palette should feel more intense than the other, unless you are deliberately trying to draw attention to one side. We have covered a lot of ground. So let's pull it all together into a workflow you can actually use. These 8 steps are designed to replace gut instinct with a repeatable process, something you can come back to every time you make a color decision. We'll go through 4 steps now and pick up the rest on the next slide. The step 1 is defining the variable. What does color actually represent in this chart? Before anything else, be specific about what attribute color is doing the work of encoding. Step number 2 is defining the task. What do you need your viewers to do with that color information? Are they comparing two groups, spotting a geographic pattern, following a trend over time? The answer shapes everything that follows. Step number 3 is choosing a palette family. Using the taxonomy we have built up, pick the right family for your data type and task: categorical, sequential, diverging, and so on. Step number 4 is tuning the perceptual properties. Check the details. Does the lightness gradient actually progress smoothly and consistently? Are you or your categorical hues distinct enough at the sizes they'll appear on screen or in print? Here's the important thing to notice. These 4 steps happen before you look at a single color name or hex code. Get the thinking right first, and the actual color selection becomes much more straightforward. You will know exactly what you are looking for. Now for the second half, steps 5 through 8 are where you verify and finalize your choices before anything goes out the door. Step number 5 is checking accessibility. Strip out the hue and ask, does this still communicate? Run a grayscale test. Then simulate common color deficiency conditions. If the chart falls apart without color, it needs more work. Step number 6 is checking semantics. Do your color choices line up with what your specific audience already expects? Red means lots in finance. Red means high in meteorology. These aren't universal rules, they are domain conventions, and they vary. If your palette clashes with an established expectation in your field, resolve that conflict before you publish, not after. Step number 7 is testing in the real environment. This one gets skipped more than it should. Your palette needs to be evaluated on the actual background, screen, projector, or printed page it will live on, not just on your design monitor under ideal lighting. What looks balanced in your application may look very different in the room where it matters. Step number 8 is document and standardize. Write your color mappings down in a style guide. Every future chart in the same project should draw from the same system. This step is easy to skip when you are working on a single chart, but consistency across the whole collection of visualizations matters just as much as any individual palette decision. It's what makes a body of work feel coherent and trustworthy. And that's the full workflow. It's yours to use from here. Let's close with the one idea I most want you to take away from today. Every color in your chart should earn its place. Color isn't free, it costs your viewer mental effort to decode, and if that effort doesn't pay off with real information about the data, you haven't added clarity. You have added noise. That's the core principle everything else today has been building toward. So as a final summary to carry with you, use hue for categories. Use lightness for order and quantity. Use saturation to direct attention. Avoid rainbow color maps as your default for continuous data. Never use or never let color be the only thing carrying a critical piece of meaning. And always test your palette in the real environment where it will actually appear. Until we meet again, here's a small challenge. Find any three visualizations you come across this week, a news graphic, a work report, a social media post, and evaluate every color choice against what we covered today. You will start seeing things you can't unsee. That's a good sign. Let's meet again.